So for manufacturing technology 2, we had a project where we have to come up by simulating using flexing. We have to simulate up to 50,000 flanges in 1 month, and we have to do the necessary calculations for it as well. So going straight to the topic, for chapter 1 we did material selections. So material selection, we had to choose between stainless steel A350 and also carbon steel A105, and we saw the service conditions and all that. Carbon steel A105 is able to utilize for pressure systems of high and ambient temperature operating conditions. It was also harder and stronger, more rugged, and also suitable for industrial usage. So based on all these reasons, it was a smarter choice to choose carbon steel A105 as our preferred material to manufacture the flanges. So to manufacture a flange, there are actually many metal processing techniques. So the one that we researched was casting, forging, powder metallurgy, and also machining. So we actually categorize to choose the best processing technique. What we did was we categorized it into a few different criteria, such as besides the description of the process, we also talked about dimensional accuracy, the operation time, the mass production cost, and also the advantages and the disadvantages, the limitations basically. So when we're talking about all those things, the powder metallurgy method was able to produce nearly near net shape and of very high accuracy. The operation time also was very quick, as it's a fully automated process and no material removal is required. Furthermore, the mass production cost is very low because of the capital cost is divided into a big volume of the part production. And advantages, it's improved fatigue resistance, the chances of voids are reduced, and greater strength as well. However, for our design, it required some high accuracy in the end. So we had to also choose machining, as it includes high accuracy where it depends on the labor skill and experience, and although it requires a longer time to do the manual processing, it was acceptable. And so we decided to go with powder metallurgy and also machining at the last part. So we decided to choose the powder metallurgy and machining as the secondary process to produce the flange due to the design considerations which are available in the powder metallurgy process. As we can observe in the picture, the flange part has a hole perpendicular to the direction of the part, and this is not possible to be done with powder metallurgy process, only because this process is only able to produce holes and grooves which are parallel to the ejection direction. Hence, the machining process has to be included for the manufacturing process. So powder metallurgy and machining are both able to provide very good, great dimensional accuracy, because the powder takes the form of a metal die and the produced hole is done by the automated milling process. A near net shape product is produced by the powder metallurgy process even after the sintering process. This near net shape feature is currently extremely essential, as flanges are to be designed for very specific components with specialized functions, thus making accuracy a very major requirement. So in order to produce this 50,000 units as our target, we should consider 24 hours continuous shifts with 6 working days in 1 week, which will average to about 87 units per hour, making it a large volume manufacturing process. So the amount of time spent due for the manufacturing of each flange is critical in order to achieve the target. From a production point of view, manufacturing cost plays an important role in deciding the metal forming processes, and based on the requirement of the mass production to achieve the target, powder metallurgy was the best option. Casting, which has a low manufacturing cost, is not able to deliver in terms of large volume and becomes expensive when a large volume is required. So although the capital cost for powder metallurgy is high, the long-term factor and the production rate factor should be taken into consideration, and these two factors allows us to achieve a relative cheap price per piece when compared to other available processes. Although machining will significantly increase the cost, it is acceptable as we need to produce a product with great dimensional tolerance. Hence, machining must be added as a secondary process besides powder metallurgy. Stronger metal bonds are produced, which provides a greater strength due to the sintering process in the powder metallurgy process. These bond formation results in the development of grain boundaries for each particle, which reduces void on a microscopic scale. This helps to reduce defects in the final products, which prevent unnecessary losses in the production, and improved fatigue resistance is achieved due to the preheating and heating steps, which result in a longer product life. All the above advantages which have been discussed proves that the decision to choose powder metallurgy and machining was the best option in mass producing these flanges. So now I'll be passing it to my colleague. Thank you.
Assalamualaikum. Now I will talk about the specification and standard selection for our materials. So based on American Society for Testing and Materials, we decided to use ASTM standard of A105, which consists of elements of carbon, manganese, phosphorus, sulfur, silicon, copper, nickel, chromium, molybdenum, and vanadium, mixed with the steel in the material. So when these elements mix, it produces a minimum of tensile strength of 485 megapascal, minimum yield point of 250 megapascal, thus producing minimum reduction area of 30% and maximum hardness of 187. So ASTM A105 is the most suitable choice, especially since the usage is standard for use in a pressure system which has an ambient and high temperature operating condition. So this is the most suitable element that we can use to produce our flange. Now I'll talk about the process details to produce our flange. So we decided to use powder metallurgy and machining for our process. So for powder metallurgy, we first will mix and blend all the product or elements together using V-type blending mixer with blending pedal, and at the same time this process will give a better homogeneous mixing of the powder materials. This process is done to gain a uniform distribution of particle sizes and to reduce porosity. In this process, the carbon steel powder will be loaded inside the mixer and blended by the blending pedals inside the V-type mixing machine, and we suggest and decide to use the Higal Tech V-shaped mixer with blending pedal VBM200 with 300 liter loading volume. Then we will go to compacting process with its dry pressing, and its dry pressing, the powder will then put into a mold, then will be pressed under high pressure to produce the shape of the product. After that, we will go to the process of sintering. After the product is placed under high pressure in the mold, then we will go and sintering process on the conveyor belt to form taking the metal in the form of powder and placing it into a mold or die. Once compacted into the mold, the material is placed under high heat for a long period of time. Under the heat, the bonding will take place between porous and great particle, and once cooled, the powder will be bond to form a solid piece. That's all for the sintering process. Now I'll pass to my colleague to tell about machining and inspection process. Thank you.
I'm going to talk about the last two processes in this particular production, which is the flange. The last two process, which is the machining and inspection. The first one, machining, we decided to use CNC machine, which gives better quality product to achieve realizable goals. Development of CNC machine are considered as an outstanding contribution to machine tools engineer. Intelligent use of CNC machine tools can achieve complex engineering tasks. The first process in the CNC machine, which is the CNC lathe, to use for facing, turning, and chamfering. For the second part, which is the CNC drilling machine, used for drill the hole and burning. The last CNC machine, which is the milling, to make the last touch and surface finishing. This all then complete the overall manufacturing process of the flange. Last part and one of the important part, which is the inspection. To ensure we are following the standards and the customer requirement, we must examine the end product during and after the whole manufacturing process. And non-destructive test is helping, NDT is helping to control the quality and quantity of the product flange. The dimension inspection is done next by inspecting the outer and inner diameter, bolt circle and bolt hole diameter hub diameter, and as well thickness of the weld end, length of the hub, and the strengthness of the bolt hole. These specifications are very important to inspect during the manufacturing of the flange. And there's two machines we have decided to use also for inspection. The two machines were used to undergo hardness and accuracy. So the Vacker's hardness test, fully automatic, is used to test the hardness of the product part third. So the last inspection method that we had decided to use would be the accuracy test. For this test, we decided to use the Duramax contacted measurement machine. This machine is used to ensure the reliability of the measurement result for the product flange. By the inspection, the last part for our product finished the process for the flange. Thank you very much. I pass to my colleague.
Alright, so we're talking about the calculation and the flexing simulation. Going on, and from there we choose the flange dimension, which is from ANSI system. Then we do a small calculation here. After that we got the flange volume, which is 238.4 centimeter cube. Then this is our standardized. Okay. Next we'll be going to the mixer calculation. Okay. So first thing we do the production capacity after we choose which machine we're going to use. Then we got the volume, which is 150 per liter, and our machine went for 20 minutes. We choose the worst case scenario, that will be 20 minutes, and we can get the 0.45 meter cube per hour. Then using our flange volume, we can get the rate of production, which is 1188 piece per hour. From there we can get the cycle time, which is 1.589 times 10 to the power of -3 hours per piece. Okay, that's all for the mixer. Oh yeah, I forgot. That's our setup time. Setup time is we choose for 3 minutes per cycle, which is convert to hour with 0.05 hour per cycle. And we already choose our scrap rate, which is our defect, which is 10%. Then we're going to do the pricing calculation, and we're going to same with the before. We can get a production capacity. Then for the pressing, we got 720 piece per hour. Then the cycle time is we can get 0.00278 hour per cycle. Then going to the centering furnace. Okay, same. The formula is the same, so we can get the production capacity, which is 60 piece per hour. The cycle time we can get 0.01667 hours per piece. Then the setup time, there's no setup time because it's a continuous process, and there's a continuous moving conveyor inside the centering machine. And next we're going to talk about the CNC. In CNC, okay, we can get the production capacity around 750 piece per hour, and the cycle time is we get 0.001333 hour per piece. Then we get we choose setup time is 120 seconds per piece, so it's 0.00333 hour per piece. Next, we're talking about the inspection machine. Inspection machine we choose per piece. The proximity is the 30 seconds. This means in one piece we do 30 seconds of inspection. So we convert that and we can get the 120 piece per hour. The cycle time we can get 0.00833 hour per piece. Then moving on, we were talking about the calculation for number of machine for the entire process. So in the present production, we choose 4 weeks per month, 6 days per week, and 3 shifts per day for 8 hours a shift. Then we calculate that all with the reliability for production is 90% and reliability for setup time is 100%. So we can get the 80 production, which is 518.4 hours per month, and for setup we get 576 hours per month. So moving on, we're going to calculate how many mixer machine are we going to use. See the production, we choose a Q total for 55,000 per piece per month, because we choose 10% of defective, so input that is 5,000. Then before we already calculate the cycle time, then we can get the WL, which is the formula is Q total time is the cycle time, and we can get 87.395 hours. Then we get how many production we need. So 87.8395 divided by 518.4, and we get 0.169. Then we calculate the setup. Then we get the end setup is the 0.076. So we total about the end production and end setup. So we can get 0.1762. Hence, it's the bare minimum. We need one mixer only for the production of the flange. Moving on, we calculate the for pressing. Same as before. We can get the end production, which is 0.147, and N for setup is 0.0265. Then we total both of them, we can get 0.174. So we only need one pressing machine. Then for the sintering furnace, okay, for the end production we get 1.76. For setup, there is no setup, so it's 0. We total the end total and we total the production and setup, we get 1.76. So from there we need 2 sintering furnace for the production. And when talking about the CNC, here we can get the same. End production is 0.1414. Then setup we get 3.179. Then we plus both of them, the production and setup, we get 3.321. So there's 0.3. So bare minimum for production we need 4 CNC. And then for inspection, the production is 0.79. For setup is 0 because there is no setup time. So total is 0.79. So required machine is only 1. So that's all for the calculation. So moving on, I will be talking about the flexing simulation. So before this, we do the calculation how many machine we need. So from this setup, we can see that the source, then Q1 and the mixing machine. Then we get the Q2. Then there's the compacting machine, which we connect to conveyor to connect them to Q3. After that, from Q3 there's a split for centering 1 and centering 2 because we need 2 machines for centering. Then from centering is the continuous motion of conveyor going to next Q up. This is a Q4. At Q4 we split it into 4 of CNC, which operated by the operator, 1 person per machine. Then after the CNC, after done from CNC, let's go to Q5, sorry. Okay, the flange we go to Q5. From there, we only need for 1 inspection machine, so there's only 1 inspection. After that is the sinks. So that's all from me, talking about the mixing, talking about the setup of the machine. So from the simulation, what we get is the stay time result and the throughput result per hour, and is the state pi. From there we get is the calculation of the how many can produce a flange. So from the simulation we get 57,000 of flange per month, which is more than the required number, which is 50,000. Okay, that's all from me. Thank you. Then I pass it to my colleague.
So let's talk about costing, so that we can eventually lead to the price per unit. So there are 4 important things that are to be considered in our calculation for the price per unit. The first one is the material cost based on the standard of ASTM A105. The second part is the machining cost to run during production. The third one is the wages cost towards the workers. And finally is the renting price that we have to pay for the site of our manufacturing place. So moving on to the first one, which is the cost of material. So if you were to refer to the table based on our standard ASTM A105 that we need the materials with, it will and calculate, we can come to a conclusion that it will cost us around 4 ringgit 73 cent per unit kilogram for the materials. So once again, to recap, we need around 4 ringgit 73 cent price based on our ASTM A105 standard to cost per unit kilogram, which roughly translate to 487,537 ringgit for 55,000 part of flanges. This is only the price for the materials. Now moving on to the second and third part, which is the workers' wage and the energy calculation wage to run the machine, it will come around to a total of 131,324 ringgit. So that is 3 of the costs that we need. And finally, to conclude, this is the price that we need for the renting of the place of the site, which is on 65,000 ringgit per month to rent. This will all come to a total cost of 618,861 ringgit. And to find the production unit value per piece, we divide it for the total number of flanges that we use. So 618,861 ringgit will give us a final production price per unit flange of 11 ringgit and 25 cent. Thank you very much indeed, and that is all about our project.
I am Ali.
Imran.
S.Kugen. Shafiq.
Mirza.
Thank you very much, Dr. Mazdi.